and welcome back to Power Electronics. In this video segment, we're going to examine a buck converter design, and we're going to split it into two parts. This first video will cover the first part, and in that one, we're going to look at sizing the components. A lot of the material that we use for the buck converter and the power stage can be found in this application report by Brigitte Hauke from TI, and I have the link here, and I will link it into the description as well in this video. Quick overview. We're going to look at design requirements and specifications, and this is a somewhat made-up design, but realistic in the numbers we're using. We're going to estimate the switching duty cycle based on the input-output voltages. We're also going to estimate the output current based on the power requirements that you'll see in the requirement specifications for this design. And from there, we're going to look at sizing the components, and there's four basic components we're going to look at. We're going to look at sizing the inductor, then the capacitor, then the diode, and the MOSFET. And when you go through a design, they don't have to be done in this order. This is typically the order that I do them in, but design is a very iterative process, and even as I was making this video, I was looking at maybe I should choose this component over that component, and I'll describe some of those scenarios when we get there. So let's look at the requirements for this design. For this one, it's a DC to DC converter, and we have 15 volts as the nominal input, 5 volts as the nominal output, and it's a 10-watt power supply or a 10-watt DC to DC converter. I'm using nominal values, and those are more of a requirement, and I'm not really providing detailed specifications around these numbers. In a more formalized design, we would have firm specifications. So for example, we would limit the input voltage with a plus or minus voltage rating, likewise with the output. And we would probably have a not to exceed output power value. And finally, the one last requirement is would like to see that efficiency be at about 90%. Once we put that efficiency at 90%, that is going to push us into the realm of a switch mode power supply like the buck converter is that we've been investigating over the past week. I'm going to make a couple assumptions. I'm going to assume we're going to do a continuous conduction mode for our buck converter. Again, we are going to be in a switch mode power supply. And using the 10-watt output, I can compute an average output current equal to 10 watts divided by 5 volts. And that's going to give us a nominal output current, which is equal to 2 amps. So we'll be able to work with that in our design. And we can also estimate the duty cycle based on our input and output voltage. Recall that our output voltage Vout is equal to the input voltage times the duty cycle. Therefore, Vout divided by Vin will equal the duty cycle. Again, this is just an estimate. Oftentimes, we are going to be using some form of controller to regulate and automatically adjust the duty cycle as the input-output voltages fluctuate with loading. And using this as an estimate, we see that we have 5 volts divided by 15 volts, and that gives us a duty cycle of about 1/3 or 33% is what we can estimate for our duty cycle. Now let's go on to sizing the inductor based on this. You'll notice that in the requirements, we did not have a specification for the ripple current through the inductor. A standard rule of thumb is our delta I should not exceed well, let me say delta I over I out should not exceed 40%. So we do not want to exceed 40% of the output. I'm going to be more conservative, and I'm going to start with a delta I equal to 20% of our output current. So 0.2 times 2 amps will give us this ripple current through the inductor, and that's equal to 0.4 amps. We also were not given a switching frequency. I'm going to try to use a smaller footprint, and I'm going to want to push our switching frequency up higher. So without a switching frequency, and sometimes the switching frequency is going to be mandated to you, I'm going to assume a switching frequency of 500 kilohertz. With the switching frequency and the ripple current and our known output voltage and our estimate of our duty cycle, we can compute the inductor using the following equation. L is equal to V out times 1 minus D divided by Fs times delta I. Putting those numbers all in place gives us 5 times 2/3, all divided by 0.5 EE6. I'm writing our frequency for our switching in megahertz, which is going to provide our numerator in microfarads. So there's a reason why I wrote our switching frequency in that form. Times delta I, which is 0.4. We see that our inductance is equal to 16.6 microhenries. So that's going to give us a range for our inductor. Before we select an inductor, we also have to look at the average current that is going to be flowing through the inductor, because the inductance value itself and the current flowing through the inductor on average are what will help us size that inductor properly. Let's go to sizing the inductor. Using a search engine such as found in either DigiKey or Mouser, I did a quick look for an inductor in the 22 microhenry range, and we see right here we have one that's 22 microhenries, and it was a Bourn, and I have to also look at the current. That's the other spec we need to look at, and the rating on this device was 6 amps RMS for the current. And because we are at nearly DC, 6 amps RMS will also exceed our current requirement of 2 amps at DC. The downside to this one comes later when we do the power analysis or the efficiency calculations, and it's the equivalent DC resistance due to the windings. And I'm going to use the worst case values. We see we have for the 22 microhenry inductor, we have 72 milliohms of DC resistance. Remember, my computation was originally 16.6 microhenries, and I'm thinking sizing up. But I also assumed a 20% ripple current. If I size down to 15 microhenries, we'll increase our ripple current slightly. It won't be greater than 40%, but we'll reduce our DC resistance to 50 milliohms. And that might help with our efficiency. It's just something to keep in mind as we're going through the process. Do I want to increase the efficiency at the expense of a higher ripple current? Let's move on to sizing the capacitor. The capacitor sizing straightforward. C is equal to delta IO divided by 8 times the switching frequency times delta VO. A ripple voltage was not provided to us in the requirements or specifications. I'm going to make an estimate and assume that 5 volts plus or minus 0.01 volts or 10 millivolts should work well for this design. Again, I'm filling in the blanks on the design, but it's something you sometimes have to do at least to get a first cut at the values. This gives us a delta V out of equal to 0.02 volts. Sizing the capacitor using all these values, we see that C is equal to 0.4 divided by 8. Again, I'm going to write our switching frequency as 0.5 megahertz, so 0.5 EE6 times 0.02. Doing these calculations, we see that the capacitor value is equal to 5 microfarads. Again, we may go up or we may go down. I'm going to go slightly down, which means our ripple voltage at the output is going to increase slightly, but I'm going to select a 4.7 microfarad capacitor, and I'm going to size it at 35 volts DC. So that's a typical size. You'll find capacitors in ratings of 35 volts, 50 volts, 100 volts. Our output is only going to be 5 volts. Our input is only going to be 15 volts. So this is a pretty good range. I believe I decided on a TDK C series. And again, I will link the data sheets in the catalog for this. This TDK one that I selected is a multi-layer ceramic chip style capacitor. I am doing all surface mount components on the selection process here. Okay, we've got the inductor sized, we've got the capacitor sized. Let's look at sizing the diode. Because our efficiency spec was 92%, I'm going to go for a Schottky diode, which I don't have shown here, but I'm now going to show there. So I'm going to go for a Schottky diode. Its average current rating has to be equal to 2 amps times 1 minus D. And that is the average value. If I average this current over one whole switch frequency, that's the number we would get. If I design for 2 amps, I'm going to be safe. Our maximum repetitive voltage for the diode has to exceed 15 volts. And with the Schottky, we'll have a very low forward conduction voltage, and I'm hoping that this is going to be less than 0.5 volt. Again, trying to reduce our conduction loss when the diode is conducting. And recall, the diode conducts when the MOSFET is open during the second half of that switching period. That second half. So again, I went to Mauser. Some people like to use DigiKey. And going for a surface mount, this is the device I selected. The link is in the description below. You'll see, and this is a little bit, not a little bit, this is pretty misleading that it has a 30 amp average forward voltage. And up here it says 5. And I'm going to talk a little bit about that. But it does have an ultra low 0.3 voltage drop in forward conduction. So that is really nice. The other good thing about Schottky diodes, I do not have to worry about reverse recovery. It's a majority carrier device. And so we don't have the recombination of holes during the turn off phase of this diode. So again, fast, no reverse recovery losses in Schottky diodes. And this one's going to work pretty good. But I want to come back to this 30 amps and this 5 amps and see what's going on with this device. So here's more from the data sheet. Again, the data sheets are linked below. And this graph here is really interesting. This is a surface mount device, and it talks about ambient air temperature. And we have talked about 85 degrees C as our industrial spec. And if I come up on this device and then follow across, we see what our true average forward current rating is for this device. And that looks to be about 2 amps, which is right where we are for our designs. And our average amp's going to be slightly under. And the other thing to look at is our instantaneous forward voltage is dependent upon our forward current. and we'll see we have a forward voltage that is around 0.3 volts if we allow the ambient temperature to go up to 125. So we will be in range for this device. You have to dig into the data sheets on these devices when you're doing your design. The devil is in the detail. We have one last component to size, and that is the MOSFET. So let's go size the MOSFET. First, we're going to look at the average current through the MOSFET. Here we see that the average current, while it is shorted out or conducting, here we notice that our drain to source voltage is near zero. Matter of fact, that voltage is equal to our drain to source current times our drain to source resistance while it's conducting. But we look at that value, and it's 2 amps. It's our average value through the inductor. But the average value that the MOSFET will have is going to be I/O times D. Again, if we average this over the total switching period, we would get I/O times D, and that is equal to, for this example, 2/3 of an amp, or 0.67 amps. We also have to look at the drain to source reverse breakdown voltage, and so we're going to have to select a MOSFET that has a drain to source that's greater than 15 volts. So those are the two parameters to look at. And again, I did a search on Mouser, and there was a number of devices that came up, and I was looking for a surface mount device. And this is the part that I'm going to select for this design, and you'll see that it is one of its applications that is given is the DC to DC converter. It's a 30 volt device, and the current ratings on it are 20 amps. But again, as we saw in the diode, we're going to have to dig into the details because for all these devices, I've said this before and I'll say it again, it's our junction temperature that will determine whether or not the device is going to work in your design. If we can keep that junction temperature below the maximum value in the data sheet, then the device will be sized properly. Let's dig in a little bit more. I've got an expanded version of this data sheet, and I'm going to use for the next section when we look at the efficiency calculations in the next video, I'm going to use the rise time and fall time off the data sheet. And again, I said sometimes these aren't the best to use, but if we look at them, we have a turn on and turn off time of 12 plus 9 nanoseconds, which gives us a total switching on and off of 21 nanoseconds. And we're going to use that value in our efficiency calculation. If we had a slightly greater generator for a gate to source, it changes a little bit. And this was based on a drain current of 10 amps. We're at 2 amps, so it's going to be even less than 21 nanoseconds. By how much? Probably won't matter too much in our design, at least for our efficiency calculations. So that's the sizing of the MOSFET. Here's the turn on and turn off calculations. I've showed these once before. One of the things to note for this device, our threshold voltage, if you look at the data sheet on the last slide, was about 2 volts. And our Miller plateau voltage is going to be about 2 volts. So that implies that gate to source minus threshold and gate to source minus plateau are about the same, which would give us LN1. And LN1 is 0, so we would have very slow time. T2, if you recall, was the time it took to go from 0 to the threshold, actually T2 is the time it took from threshold to Miller plateau, and T3 was the time it took from Miller plateau until we were into the linear or ohmic region, and then the gate to source then started to go up to its final value. So that's our T on it. For this one, the T2 is going to be near 0. Likewise, our T6 because our plateau and threshold are nearly identical, will be near zero as well. And so most of the time we'll be ramping down and we'll be at the Miller plateau voltage for our gate to source voltage. So that's the turn on and turn off for the MOSFET. Again, we're going to assume 21 nanoseconds when we do the efficiency calculations. So let's recap what we did in this video. We used the input-output voltages to estimate the duty cycle. We used the output voltage and the output power requirements to estimate the output current. That output current I sub 0 and an assumed delta I, which I assumed to be around 20%, was used along with an assumed switching frequency. Again, I assumed a 500 kilohertz switching frequency to size the inductor. We sized the capacitor. Again, we had to make some assumptions. And we then sized the diode, and we used a Schottky for low loss. And finally, we sized the MOSFET, and we estimated the turn on and turn off times from the data sheet at 21 nanoseconds. Probably are going to be less for our application, but it's a good place to get us going for the next part of the design. In the next video, we're going to look at the efficiency and where the losses occur in this circuit. Recall one of the requirements that was put forward in the earlier slide was we wanted to achieve an efficiency of, I believe it was greater than 90%. So we want a greater than 90% for our efficiency. So thanks for watching this one, and go check out the next video for how we're going to do the power losses in this specific design.